Hey everyone, here is another project sent in by a viewer. A 3D scan of a tricky T-handle with some complex curves. He's planning to model this in CAD and then create a negative mold so he can cast the handle in epoxy resin. This scan was done with the Creality Raptor, and you will see just how sharp and clean it looks once we start reversing it in CAD. The viewer is a mechanical engineer and he is already modeled the part in AutoDesk Inventor pretty close to the original, but he's still not fully happy with it. I can see that for the bottom section he used a solid extrusion. The middle was done with patched surfaces, and I think he modeled the top using a loft command. Since the T-handle has a trisection geometry, using the loft command isn't the right approach. Instead, I will sketch out boundary 3D lines within one quadrant. Next, I will add 3D lines connected to those boundary lines to help control the surface curvature. Once the boundary lines are set, I will mirror those 3D lines across to the other sides and use them to patch in the surfaces. This is the resin print of the reverse model I made. It's actually a pull-up from a vintage car, and I'm pretty sure the original was sculpted by hand in clay. Hats off to the original designer here. It may be a small handle, but the way it sits between the finger joints and locks the grip when pulling is really impressive. That's why it's important to keep every detail of the original curves when reverse engineering. If the surface is even slightly off, it will affect how the handle feels in hand. Next, I will take the mesh file and convert it into a point cloud using Cloud Compare. The scan has about 607,000 faces, so I will use that same number for the points. Then I switch the point color to bright green so it stands out with good contrast. Then I will align this surface to the XY plane using a 3-point alignment. I will make the last adjustments in AutoDesk Inventor. When you start reverse engineering, the alignment of the point cloud is the top priority. I will crop a thin cross section of the cylinder and use a 3-point arc to identify its center. I will adjust the point cloud offset in the X and Y planes so I can mirror the geometry with micron level precision. Next, I will align the point cloud in the vertical plane by measuring the angle between the cylinder and the Z-axis. Finally, I will draw two arcs at the tip of the handle to determine the rotation angle between the handle and the X-axis. Remember, if the scan data isn't aligned properly, the reverse engineer will fail. Next, I will create a new part, make a 2D sketch on the YZ plane, and start tracing the profile with lines and arcs. You can see how sharp and clean the scan data from the Raptor is. It makes precise tracing much easier. By applying a tangent constraint to one of the curves, it can eliminate sharp edges on the surface. At the intersection point of the lines, I will split them apart. Next, I will create another sketch on the XY plane, project the endpoint from the previous sketch, and trace the top profiles. Next, I will create a plane at the end of this curve, draw a circle, and trim it down to a quadrant. Next, I will make a new 3D sketch, select two of the curves from my 2D sketches, and create an intersection curve. Next, I will create a 2D sketch on the XZ plane and project the endpoints from the previous sketch. Remember to always apply a tangent constraint for a smooth surface. Now the boundary 3D lines are complete. Next, I will create a new 3D sketch, include all the boundary curves I made earlier, and then break the link from the original sketch. Now I have all the boundary curve in one place. The reason I break the link is so I can split the curves exactly where I want. Then I will select all the curves and lock them. In the same 3D sketch, I will create a spline by snapping its endpoints to the boundary curves. Then I will add 2 control points to this curve and adjust them so it fits the point cloud surface. Some curves may need 2 control points, while others might require 3 to 5 depending on how much the surface shape changes along their length. This is the main reason to reverse engineer with point clouds instead of meshes. Point clouds let you see and adjust splines with the highest precision. You will need to orbit the viewport often to check curve alignment, so I recommend using a space mouse. It's faster and helps extend the lifespan of your regular mouse. The number of 3D lines needed to shape the surface depends on the surface itself. With practice, you will know exactly where to place them and how patched surfaces behave. There are 2 ways to move a control point. You can drag it with the mouse, which constrains the movement to a plane, or use the gizmo to move it along a specific axis or plane. Always remember to split the 3D curves at the intersection points, otherwise the patched surface won't work. You may notice that the Raptor point cloud looks thinner and cleaner compared to the ones from a River Point scanner. Next, I will start creating patched surfaces using the 3D lines I have made as boundaries. Then I will orbit the viewport to check how well the created surface aligns with the point cloud. Now I can see a gap in this area, so I will add another curve to control the surface here. Then I will repatch the surface and check the alignment again. I can still see a slight gap over the point cloud, so I will add another curve in this area. Then I will continue patching the rest of the surface. Always check the alignment before moving to the next patch. It's much easier to adjust the curves at this stage. Patching is one of the easiest tasks in this modeling process. You just select the boundary curves to form a closed loop. Because a Miller patch surface can be used to create solids, I will mirror the 3D curves instead. First along the XZ plane, then along the YZ plane. Now I have got all the 3D curves needed to build the entire handlebar. The next step is more labor intensive, using the mouse to pick the boundary lines. This isn't the first time I have reversed a part like this. The designer sculpts the clay model by hand, then sends it to me for 3D scanning and conversion into a CAD model. Human ergonomic industrial parts can't really be designed directly in CAD. They need to be sculpted by hand first. With all the surface patches sealed, I can now convert the model into a solid, ready for further work on the rest of the handlebar. I will use the extrude command for the bottom cylinder. Since I don't have a steel rod to test, I will create an M6 female thread instead. You can print female threads directly with a resin printer up to M4 size, but they won't be as durable as using a blast insert. Actually, the weaver intends to make a negative mold and cast it in place with a steel rod. But I think printing with resin would be quicker and cheaper for a small part like this. Here's the reverse engineering result. This part isn't very difficult to model using surface modeling tools, which are widely available in most professional CAD software. Some may ask why I don't use specialized reverse engineering software. The reality is they have very few users. They couldn't survive as a full CAD platform, and instead they target 3D scanner users. Their performance is generation behind professional CAD tools, and in practice, professionals don't use them. Because professionals can already model any shape with their existing CAD tools, there is no need for specialized reverse engineering software. It shouldn't exist at all. I'm going to print this on the Phrozen Sonic 16K using automatic alignment and medium-sized supports. The total printing time is about 2 hours, and I can fit more than 10 pieces on the build plate without increasing that time. Here's the printing result. There are a few dimples from the supports, but those can be easily sand out. The M6 thread fits fine, but resin isn't abrasion resistant. Using epoxy to glue the steel rod in place would be more durable solution. Alright, thanks you guys for watching. I'll see you in the next video.